Sorry about that interruption. The trials and tribulations of many people working from home and all the noises that occur. So we are back with example 2, and we're still looking at solving for time. And now I'd like to look at some examples from start to finish and how we solve for time using the compound interest formula. So example 2 says, how long will it take $2,500 to grow to $2,880.76 at 5.6% compounded quarterly? Alrighty, I see that I have a compound interest formula question because of this word compounded. So I know that I'm going to be using our handy dandy formula F equals P 1 plus I over M to the MT. And just like always, I'm going to pull all of the numbers out of the question and substitute it into my formula and solve for the one thing that I don't know. All right, so clearly I'm looking for how long. That's what I'm looking for. So my unknown is T. T is my unknown. $2,500 is what I'm starting with. So my present value is 2,500. Future value is 2880.76. And I'm content with the fact that P is 2,500 because it should be smaller. It is the money without interest, and the future value has the interest on it. My interest rate is 5.6%. And I'm compounding quarterly. All right, so now I'm going to take all of those values and place them into the formula, do some substitution. So here I go. We have 2880.76 as my future value. My present value is 2,500, and my interest rate is 0.056 over 4 to the 4t. All right, now let's go through the steps algebraically of what we need to do to solve for our t is what we ultimately want to go to. I want you to simplify this. So I want you to find the answer to what's inside the brackets as your first step. So I'll just rewrite that. 2880.76 equals 2,500. And then I'll find the answer to in the brackets, 0.56 divided by 4 plus 1. So it is 1.014 to the 4t. And then because we only know one law of logarithms, your next step is to divide by this 2,500 on both sides of the equation. You have to isolate this power to be all by itself because we don't know all of the rules of logarithms. We only know one. So we'll go 2880.76 divided by 2,500, and that gives us a decimal of 1.152304, and that is equal to 1.014 to the 4t. Now happy am I because I have now a number on one side and a power on the other side. And now this is algebraically where you take the log of both sides. And once you've taken the log of both sides, you know that this exponent can come right down to the front. So I can rewrite this as the log of 1.152304 equals 4t log 1.014. And now I'm going to divide both sides by log of 1. I'm going to divide by this here on both sides of the equation to get my 4t isolated. So 4t is equal to the log of 1.152304 divided by the log of 1.014. And I'm going to get an answer for 4t. So we'll take the log of this answer divided by the log of 1.014. So I get 10.19667578. And because there is a 4 out front, I know that this is quarters. And then our last step is to solve for t. And to do that, I'm going to divide both sides by 4 to give me 2.549168944. And remember that when we solve for time, that is a value in years. All right, and then we're done. So let's try this a few more times because it is one of the more, I think it's the hardest of all of the variables that we need to find using algebra. So let's do a couple more examples that are a little bit different, that will solidify your understanding. All right, it says, how long does it take money to triple if you have secured an interest rate of 7.25% compounded semi-annually? All right, so again, I'm looking for time because the question is asking for how long. I see that I have a compound interest formula question. So I have this future value is equal to present value, 1 plus I over m to the mt. I have an interest rate that is 0.0725, and I know that m is equal to 2. Now, what I don't know are my future value and my present value. They've been completely left out of the question. All I know is that my money has tripled. So this is a situation where you can use whatever values you want as long as your money is tripling. So you could use, a p-value of $10, and then your future value is $30 because it's tripling. Or you could use a start amount of $100, and then if you're tripling, it's going to have a future value of $300. Or the simplest version of this is if you start with $1 and you're tripling it, then your future value is 3. These can be any numbers that you wish, except with the one clear condition that whatever the p-value is, the f is 3 times as much because our money has tripled. All right, so I'm going to use the easy numbers. So this is 3 equals 1, 1 plus 0.0725 over 2 to the 2t. And so this is simplified down. 1.03625 to the 2t. Now we don't have to worry about that 1 in front because when we divide by 1, it doesn't change anything. So that just really simplifies everything for us in this particular case. Now I can take the log of both sides. So I can take the log of 3 and the log of the 1.03625. Again, I can now say, I'm going to bring my exponent down to the front, and that leaves me with log 3 is equal to 2t times the log of 1.03625. I'm going to solve for 2t, and I'm going to solve for t. I'm going to divide both sides by the log of 1.03625. So I'm left with log 3 divided by the log of 1.03625. Punch that in my handy dandy calculator. And I get 30.85259.212 semi-annual. And I know it's semi because of the 2. Now lastly, I can find time in years by dividing by 2, and I see that it takes 15.42629.606 years for my money to double or triple. All right. Now I'm going to do one more example with you. And then I'm going to set up your project that is posted online, because after this lesson, you are able to do the project that is online. All right, so example 4 is what the project is about. So it says, how long does it take $25,000 to double at 6.1% compounded annually? All right, so often when we're talking to folks about money, in particular, we care about when our money has a chance to become double what it used to be. So let's solve this problem using the formula. So our formula is F is equal to P 1 plus I over M to the MT. And we know that we're starting with $25,000, so that's our P. We know that our I is 0.061, and we know that M is annual because it's 1. And we're looking for how long for it to double. So we know that our F is going to be double the 25,000. So it's going to be 50,000. We'll substitute everything into our formula. And we will do our first step, which is to clean up the brackets. We will do our second step, which is to divide by the 25,000. So 50,000 divided by 25,000 is 2. Then we will take the log of both sides and bring our exponent down to the front. And then we will solve for time, excuse me, by dividing both sides by the log of 1.061. And what do we get? We get 11.706222211 years. All right, this is the exact answer. This is how long to the exact day, if we wanted to find, that it would take for our money to double. But often when we're communicating to people, we care about estimation. There is a rule. It is called the rule of 72. And this, my fine folks, is what the project is about. You are going to investigate this rule of 72, and you're going to see why this rule of 72 works in the project. Okay, what does this rule of 72 say? Well, it says that the time it takes to double, so the double time, is equal to 72 divided by your interest rate as a percent. All right, so let's just see if that's true in this case. So our double time is equal to 72 over, what is our double time percentage rate? It is 6.1. All right, so if we punch that into our pocket calculator, 72 divided by 6.1, we get 11.8 years. All right, so what was the exact answer? Why, it was closer to 11.7. But this double time estimation is often good enough for our purposes when we're communicating with folks about how long it's going to take for their money to double. And so let me show you. Oh, by the way, please omit example 5. We're going to address that in Math 53. And similarly, please omit number 6. That will also be addressed in Math 53. And also, please omit this compounded continuous investigation. This is an extension. It's always been an extension that I do with my classes if I have enough time. So you are able to do all of the student practice that is in this particular lesson, and please omit 8, 9, and 10. All right, so what I want to point out to you is that, or I want to talk about real briefly, is that online you have a project called an investment project. And you are going to do this project in Excel. Now, the instructions are online of how you program your formulas into Excel, but if you have any trouble, please do send me an email. What you are doing is you are creating spreadsheets to see how long it takes money to double at different interest rates. And by the end of the activity, you are supposed to be able to come up with that double time is equal to 72 over I in a percent version. That is the whole goal of that activity. I want to be, usually this is done very well. I've used it for the past 6 or 7 years. I just want to be very clear that you save all of your spreadsheet work, because if I'm ever taking marks off for this project, it is because the folks have not saved all of their different spreadsheets where they're showing me their work, and there is a place to upload at the end in the assignment. And again, as you're reading through this, if you have any issues, please do send me an email. But you are perfectly capable after this particular lesson of going in and tackling this online investment project in Excel. All right. Thanks so much, folks. I'll see you again for the final lesson in compound interest on solving for interest.